Okay, so welcome to class. There's a fairly low number of students today. I don't know what the reason is for that, but someone just please remind me at some point during the lecture to post the attendance code. Okay, so with that out of the way, so Prof. Kotu informed me that you did have like there were connectivity issues in the Tuesday class. So I think I have to start from doubly linked lists as far as I remember. So I'm going to start from here. Uh, Writing informatics 1B semester says 2. Oh yeah, but that's at 1 p.m. And class is important. But okay. In any case, yeah. Um, so basically, like we'll be looking at doubly linked lists. And just before we start on these, I'd just like to mention that, so basically the difference between a singly linked list and a doubly linked list is that with a doubly linked list, you can point to either direction, right? So like you have the ability, let me just actually do this. So like you actually have the ability, or rather your nodes have two links, right? So you have a node that can point to a forward neighbor and a backward neighbor. And this is very useful because, for example, if you might remember from like this week's tutorials, when we did our singly linked lists, there was the limitation that when you wanted to delete a node, you would have to have this pointer that is like a trailing pointer that just keep track of the node before the node you want to delete, so that actually let me demonstrate this so that it just remove that. Okay, so let's say for example you have well, let's just use this. Let's say you have something like this. Um, so let's say you have like this, you have a node here, and then this node points to that one, and then you have, you know, this a neighbor, and then this is and so forth. So let's say you wanted to delete, let's add another one, and let's make this point to now, right? So let's have, like, let's say you want to delete this node here. So then what you would do is, right, you would just traverse all the way to this node. So you would create like a current pointer, and then you would use it to jump through each node until you get to the node that you're trying to delete, right? And there's two ways in which you can do this. The first one is that you could, for example, move your current pointer to the node that is before the node that you want to delete, right? So you could say, for example, you could write a while loop and then say something like, I think I can add text here actually. You could say something like while my current link or neighbor is not, you know, like the neighbor that I'm trying to delete, right? Something like that. And then, so if you did this, for example, then it means that you would obviously, so you would say something like, what's happening now? Okay, this is not really good. Okay, but so like you would say something like current is current link, right? So you just keep moving forward until you get to a point where like your neighbor is the neighbor that you're trying to delete, which means that this loop would actually stop when you get to this node here that is before that node, right? And then what you would do then is you would change this node so that its neighbor is that node. And then, so effectively, like basically deleting this connection here. So you delete this connection and then make this node basically, you know, like have that as a neighbor. And then now you have these two nodes that have that as a neighbor. And then you would make this point to something like null pointer, right? So you would remove that and then instead make this point to null. And then after doing that, then you have your link, and then you can safely deallocate memory for this node, and then do your deletion and everything that you need to do, right? Or you'd need to have another node that's a trailing pointer. So you would remove this, and then you just say while current is not equal to the node you want to delete, and then this would iterate up until current gets to this point, and then you'd have another trailing pointer that then goes all the way to here, and then you would make this trailing pointer points, like manipulates so that this neighbor, like this guy's neighbor is that, and then you would delete, right? However you do it, doesn't really matter, but there's a bit of admin, right? And so you have to keep track of the previous node so that you don't lose your you don't lose this node, right? You still have access to this node so that you basically don't lose your list, right? So with a doubly linked list, so the nice thing is that then you have all of these nodes like that, but now you have a forward arrow, and then this node actually has a backward arrow, right? So all you need is this current pointer, and then all you do is you just traverse all the way to the node that you want, and then when you get there, you just basically just say that this guy's previous neighbor, right, is now that, and then this guy's previous link is null, and then this guy's neighbor is null, and then like you don't have to do like too much like thinking or like magic or like too many like considerations in order to delete a node, because you have the previous link and you have the next link, right? And then another reason it's important is obviously you can move in either direction along the list, right? So you can iterate forward and you can iterate backwards, right? So far we built like forward iterators because we did like singly linked lists, right? Where we only move forward. But then you can also build like a backwards iterator where you overload the decrement operators, right? So with our iterator classes, so far we only overloaded the increment operators, but you can move backwards in a linked list, right? So that's the whole idea behind having doubly linked lists. Okay, so every node has a next and back pointers, and and it basically can be traversed in other direction. Okay, and then so in terms of the operations, similar to the singly linked list, you still have the like initializing the list, which means you're like for example setting your front or head to like null, and like your tail or back to null, and things like that. And then you also destroy the list, and then determining whether the list is empty, searching for a given item, retrieving the first or last element, inserting or deleting an item, finding the length of the list, printing the list, making a copy of the list. Yeah, so it's basically like your linked list. You still use the same linked list ADT like functions. The only difference is that now each node, right? So when you create a node struct, like it's going to have. So if I create this, the only difference is that now I'll have a node T pointer, which is previous, and then I'll have a node T pointer, which is next, right? So that's the difference. So you have to keep track of these two links instead of keeping track of only one link. Okay, so you have the default constructor initializes the doubly linked list to an empty state, and then it sets the first and last to null, and it sets the count to 0. And then you have a function for checking if the list is empty, and then that's basically just checking if the count is still 0, right? So if it's 0, it's empty. And then you have a function for destroying the list, which basically deletes all the nodes in the list and leaving the list in an empty state. And then you have a function for setting the count to 0. Oh, no. So obviously, like this sets the count to 0, so we're about that. And then you have a function for initializing the list, which basically reinitializes the doubly linked list to an empty state. And it uses the destroy operation because this does everything, right? Deletes all the nodes, sets the head to null, sets the tail to null, and sets the count to 0. So you just simply call the destroy operation, and that's should do everything for you. And then you have the length function, which returns the count of the nodes in the list. You have the print, which traverses the list and then outputs the info contained in each node. You can also do this using your iterator. You don't have to do it like, by using like a current pointer and then just skipping through the list, like as I mentioned here. You can just use your iterator and just use a for loop, and then you have something like this. So for the iterator I is begin, I is not end, I plus, provided you overloaded the post increment operator in your linked list iterator function, and then you would do like stuff like cout dereference. This would be if you overloaded the dereference operator as well in your iterator class, and then you could do something like that, for example, and then this is how you would effectively traverse the list, right? You don't have to like do all that admin where you have your current pointer, while current is not now, current is current.next, and all of that stuff, right? You can just, if you have a linked list iterator, it just makes life easier for you, right? You can just use a for loop and it'll do everything for you. So why don't we use and? Okay, I'm confused what you mean by that. So we do use the end function here. Remember, and returns an iterator, right? And does not return like a node or anything like that. It returns an iterator. Remember, in your linked list class, the end function, so it returns an iterator, and the name of the function is end. Oh, I list an end. Well, you can't really say that unless you overloaded the less than operator in your linked list iterator class. Remember, all of these, right, are overloaded operators, right? This you don't have to explicitly overload. This is just a copy assignment operator. Remember, if you don't explicitly overload this operator in your class, C++ creates its own like copy or assignment operator under the hood, right? Which performs a shallow copy, which you don't really mind because you're not really trying to copy the like in the case of the iterator, right? We don't really have to overload this copy assignment operator, but then we do overload this, right? So you have to overload this in your iterator class, right? Because this returns an iterator, right? And then if you wanted, you could also overload this. Then this would just basically check, if the pointer for the iterator on the left-hand side basically is one position before the pointer of the iterator in the right-hand side. So you can do that, right? There's nothing stopping you from doing that. I just prefer doing this because I don't know. I suppose it's just my style of programming. In terms of linked list iterators, I just check for iterator is begin. So I start at the beginning, and while I'm not at the end, just keep moving forward, right? So it's really up to you. You can do it however you like. And then yeah, so you overload the dereferencing operator, and then so this will just return the value that's actually stored in the node, right? Remember, your iterator class keeps track of a node pointer as a private member attribute. right? So basically, when you dereference the iterator, what you're doing is you're just returning what is stored in that node's info variable, right? And then so then that would give you the actual data that you're looking for, and then so basically you just have this nice and tidy code for outputting everything inside of your list. Okay, so I hope that makes sense. And then yeah, so that's printing the list, right? So that's how you traverse the list using your iterator, and then outputting the info contained in each node. And then in terms of reverse print, so this would just reverse print, right? So in your reverse print function, instead of having like let's say I plus plus, you just have I minus minus, right? But it's the same thing. But then you would have to change these around. So for iterator, I is end, I is not begin, right? I plus plus, and then you would then print whatever you come across. But here, it actually might be risky to use not equal to, because it means that you won't print the first element of the list, right? Because remember, with and returns null pointer, like it returns an iterator where the node points to nothing, right? Because that's the end of the list, right? But begin actually points to somewhere useful, right? That's the first element of the list. So here, you might want to overload this operator instead, right? So then you might want to say, for iterator I is and I is greater than or equal to, yeah, begin I plus plus, just so that I minus minus, because we like obviously we want to make sure that we don't go like like to like a memory address that is before begin. So we say greater than or equal to begin, and then I plus plus, and then this would still achieve the results of printing everything in reverse, right? So hopefully this also shows why iterators are super useful. They're very useful for cleaning up your code, and just automating some of the stuff that you would have to like just do yourself, like keeping track of current pointers and all of that stuff. Okay, so that's reverse print. In this case, I is starting from null pointer. Yes, that is true, actually. Yeah, that's actually true. So if you say I is end, that would actually mean that this would start from null pointer. That's a very good spot. I didn't think about that. So then you could say something like, if, let's see, well, yeah, say something like that. So if it's not null pointer, so if the value that we're getting is not null pointer, then output. So that means we would essentially skip the first iteration, or we could be smart and instead of saying using the post decrement operator, we could use the pre-decrement operator, and that should help us achieve what we're looking for, because then it means we would not output wait. Yeah, we would decrement first and then output. Yeah. So then this should be fine. Yeah. Let me just check. I is end. So it's at a null memory address. And then decrement first, output, and then move all the way, get to begin. Yeah. Okay. It looks like it would work. So yeah, you can try it out. And then yeah, but it looks correct by inspection. Okay. So yeah, but good spot, very good spot. All right, and then so function search. So this would be searching the list. And you see, so the nice thing is you can't, for example, do this with a singly linked list, right? Because you don't have these backward links, right? You don't have these links that point backwards. Okay, so where was, okay, yeah. So this returns true if the search item is found, otherwise returns false. The algorithm is same as that for an ordered linked list, right? So you basically just traverse the list. Sorry about that, and then you just you return true if the element that you're looking for is there. You can still use an iterator for that. Like for example, you can like use the like traverse the list forward, for example. Let's say you're starting from begin, going all the way to end, I plus, and then you could just say if you know the value that I'm looking for. And then, so obviously this would be a search function, right? So search t value, and then you would do something like this. And then you would say if that value is evaluates to t with value, then return true, right? So you can still use your iterator for that. And then if you know you finished searching and you didn't reach this point, then obviously you would not have returned from the function. So you just return false here at the end, right? So yeah, you can do that. Okay, so front returns the first element of the list. Yeah, and then back returns the last element of the list. Yeah, okay. And then if the list is empty, both functions will terminate the program, right? Doesn't really have to terminate the program. I mean, like you could do things like you could output an error message and say, you know, the list is empty, or you could just not do anything, right? But usually it's good practice to output some sort of message, like give some sort of feedback to the user. But the point is, if you know the list is empty, then there's no front or back of the list because there's no first element and there's no last element of the list. So you can't return, you know, like a null pointer because maybe the person who's calling the function might think that this will always return some sort of useful value, and you know, then they might wind up using null pointer where they're not supposed to use it, and all of that stuff. Or in your documentation, you could specify that this function returns null pointer if the list is empty or something like that. But the point I'm trying to make is that it doesn't always have to terminate the program. Okay, so let's look at inserting a node. So there are 4 insertion cases, like in the case of a doubly linked list. So it's inserting in an empty list. So there's a specific way you handle that. There's inserting at the beginning of a non-empty list. And then there's inserting at the end of a non-empty list. And then there's inserting somewhere in a non-empty list, right? So that is like in the middle of the list, for example. And then, so case 1 and 2 require an update to the first pointer. Case 3 and 4 sort of similar. And then, so in all cases, obviously, after inserting an item, you increment the count by 1, right? So let's look at this. So this has to do with inserting at the middle of the list. So if, for example, you were to insert an item at the start of the list, right? Let's just see how you would do that. It's just okay. So let's say this is our. Actually, let's remove all of this. Remove. Okay. So let's say, for example, like what does this do? Okay. Let's say you were trying to insert an item at the start of in an empty list. So then your front pointer. What's happening now? Your front pointer would basically be pointing to null. All right, so let's just do that. So let's say that's null. And then your back pointer would also be null, right? And then you have this new item that you want to insert. Then it has a forward and a backward link, and then it has a value, right? So I'll just make this t. So then what you would do is you would basically make, you would store the address of this node in front, right? So then you would say front, literally like you would say front is the new node, right? So we create the node, new node, and then I don't think you actually need that here. And then, so you just have that. And then what you do is you'd say new node, next is, well, in this case, it's not anything useful. New node previous is also not anything useful because the list is empty. But then, and then you make the front pointer store the memory address of new node. So you literally do that. And then you would make the back pointer also store the memory address of new node, right? So you do that if the list is empty, right? And then if the list is not empty, but you still want to insert an element at the front of the list, then what you would have to do is, so you would still create the new node, but you want to insert it here at the front of the list, right? So you'd create the node, say that's the node, and then so what you would have to do is, so you basically have to say that because you can access the first node using front, then you would say like front. So you could do some, so you would create your node and then you would say, so new node, next is front. So you copy the memory address that is stored in front, you store it in next. And then because this is the first node of the list, then the previous will be null pointer. And then after doing that, then you would say front. So in order to access the node that front is currently pointing to, right, you would say then front previous is new node. And then you would change the memory address that is stored in front, and then you would store new node, right? So that's basically the logic that you would follow, right? So if you're inserting something at the front of the list, so if you're inserting something in the middle of the list, then you would have to traverse to that point, right? And then so you would basically have something like, so you'd create your node. I actually forgot to do the most important thing, which is set the value. So it would be the info that's provided as a parameter to the function. And then after doing that, then, so in this case, you can make these points to null pointer initially. And then after that, then what you would do is you would then do something like current is front, and then while current is not, for example, null pointer, then what you would do is you would say that current is current link, and then if like current or like, let's say for example you're using an index to like insert the node, then you would do something like for int I0. Yeah, so because obviously you'd have to provide an index, so I left an index I++, and then you would say like so if I evaluates to be the length of the list, or count as it's usually called. If I evaluates to the index that's provided, then like you do something, right? So you'd say, so this is where you would like do all the operations that you need to do. So if you're inserting to the middle of the list, the first thing you need to do is you need to make the node that is previous to point to the new node, right? So if I get to a certain index, then what I want to do is, so let's say this is 0, 1, 2. So this would be at index 2 before I insert this, right? So if I move to, so if I say 0, 1, 2, then that means I'm here. So then what I would do is I would basically say this node's previous is my new node. My new node's neighbor is that node. And then my new node's previous is that guy's previous. And then, that guy's previous is new node, right? So you do all those operations, right? So you basically then say, so current, previous. So I'd first have to obviously, before I terminate the link from this guy to that one, I would first make this guy point to the new guy, right? So I say current, previous, next is new node, and then I would say current. So now that I have that, then I say new node previous is now current previous, right? And then, so now I've established these two links here. So current previous is next is my node. My node's previous is now that guy, right? So that's basically what these two statements mean, right? Current previous is next is my new node. My new node's previous is that other node, which is current previous, right? And then after that, then I can say my new node's next is current, and then I can say current previous is new node, right? So the new previous for current is no longer this node, right? But it's new node, right? So I'm changing this, right? So I'm updating it. So current previous is new node, right? And then, so obviously I don't want to keep moving forward. I found what I was looking for, so I can just break the loop here, right? So that's how you would insert in the middle of a doubly linked list, right? So the nice thing, you have all these previous and next pointers. You can just change their connections around, and then you have what you're looking for. Okay, and then if you're entering, so like at the end of the list, then instead of dealing with the front pointer, you would deal with the last pointer. You would make changes to the last pointer. All right. And then in terms of deleting the list, there's also like a few cases. So the list could be empty. You could be deleting the first node in the list. So you must update the first pointer, or the item to be deleted is somewhere in the list. Then there's also a way to handle that. Then also the item to be deleted is not in the list. So here you could just output an error message to say that this item is not in the list, or you could just return from the function, because there's no point of performing any operation. And then after deleting a node, count is decremented by 1, as it should be. And then this is just like an example of deleting like 17, right? So you have this linked list here. And then, so when you delete 17, then what you do is, so you basically have to sever this connection here. So you have to make this connect to the next next node after 17, and then you have to make that next node after 17 connect to this node, and then so now these two nodes are connected. So you can just set these. Let me just do this. So you can just set those like to null pointer, so that they're all pointing to null, and then you can just safely deallocate that memory, and then you have your remaining list, right? So I always tell students that before writing the code for linked list operations, rather spend time actually drawing the thing on paper, right? So that you can follow the steps logically, right? Because if you start by writing the code, you might miss like a few considerations that you have to make, because it also matters, which connection you change first. You need to you need to change your connections in a way that you won't lose, like any node, like access to any of the nodes that you have, right? You don't want to lose access to those nodes, right? So you want to make sure that when you change these connections, you change them in the correct sequence, right? So to speak. So what I usually do, or what I usually did, like in my undergrad, for example, was I would draw the linked list on paper, right? And then when they say do the delete operation, then I would draw how I would do the deletion operation if it wasn't code, right? So if it was just a puzzle and there were diagrams and they were like disconnect these things, remove this thing in the middle, how would I do it, right? So I would literally say, I would make this one connect to that one first, make this one connect to that one, and then delete that one, and make sure that it doesn't point to anything useful, and then then I have my remaining list intact, right? And then after doing that, then you have an idea what to do in code, right? So you have an idea how many pointers do I need to create, which pointer must point to what, and all of that stuff, right? So it's very important to have a picture of this thing in your head that you are doing. Okay, so so that's deleting. So that's after deleting the 17. So that's how the list will look. Okay, and then we get to the last part, which is secular linked lists. And then with regards to secular linked lists, basically the idea with secular linked lists is that the last node of the list doesn't point to null pointer as we used to, right? But instead, it points to the first element of the list, right? So this is useful like in certain applications where you don't have like a list of things, like where you just do like a forward traversal, but you want to kind of do like a round robin type of traversal where you keep going around the list, right? So like the elements of the list, after you get to the end of, like after you get to the last element, you want to go back to the first, right? This is done a lot also like in operating systems, in like things like scheduling and so forth. Actually, in many applications that include scheduling, like you would have like kind of a round robin iteration where you go through a list of things and then you go back to the start, and then you give things like equal time, like for example, like in operating systems you would give like threads or like processes equal time slots on the processor, right? So that all of them are able to like have enough time, like to run in order to simulate like multi-processing, right? You learn more about like all of that stuff in computer science 3 when you do operating systems. But there are like lots of users for secular linked lists, right? I'm just trying to, show you guys that like they are important. At first, you might look at it and be like, but what's the point of this, right? But they do have a lot of uses in computer science, right? But the whole point behind a secular linked list is that you don't have a tail, right? So remember, with these ones, you have this um, first pointer, and then you have this last pointer, right? It's also called the front and a back, or a head and a tail. Depends on which book you are reading, right? But you always have these two pointers, right? But with secular linked lists, you only have one pointer. You only have the first pointer. And the first pointer is actually at the, so you can see here, it's at the last of the list, because it is both. Oh yeah, the attendance code. Thank you very much for reminding me that. Okay, so the attendance code is, so today is 15 October, secular linked list. That's the attendance code. Okay. Yeah, but in any case, so so like as you can see, like the head pointer is also the tail pointer. So usually the convention is to put it at the end of the list so that it points to the last elements of the list. And then you just use it to basically keep track of this point in your list. And then you can use it like to have a reference to your list, right? That's why we have these pointers in any case. You want to have a reference to some point in your list so that you always have access to your list. And you always know where your list starts or where it ends, and so forth. So operations on a secular list: initialize the list to an empty state, determine if the list is empty, destroy the list, print the list, find the length of the list, search for a given item, insert to delete an item, so copy the list, more of the same, right? But so in summary, like just to summarize everything, a linked list is a list of items, right, which are nodes, and the order of the nodes is determined by the address stored in each node, right? Remember, the address is simply the address to the neighbor, right? So that is the order of the nodes, right? It depends on the address that is stored in each node, right? And then the pointer to a linked list is called head or first. A linked list is a dynamic data structure. As we can see, we have a lot of dynamically allocated memory when we do these linked list operations. So it's definitely a dynamic data structure. The list length is the number of the nodes, right? In the list, that's like logical. Insertion and deletion does not require data movement. As you can see, we don't need to keep moving things around like with an array, right? Remember, with an array, you keep moving things around. Like if you remove an element of the array, then you have to move like things, for example, like backwards and so forth. Maybe if you also want to keep your array like ordered, you have to, do like a lot of movements, like moving things around and so forth. All right, so the nice thing about lists is you don't have to move anything around. You can just go to where you want, and then you can just insert what you want to insert there, or you can remove it from there, right? You just have to keep track of all of these links and all of these neighbors. That's the only important thing. And then searching the linked list is sequential. As you saw, you go from one node to the next, so it's sequential. The head pointer is fixed on the first node. Remember, sorry about that, the head pointer is always on the first node. And then when you traverse, you use a pointer other than the head, right? So you don't move the head pointer. You leave the head pointer where it is. You create another node. We usually call it current. And then it starts where the head is. And then it moves one node at a time, right? Then with a doubly linked list, every node has two links, next and previous, can be traversed in either direction. Insertion and deletion require the adjustment of two pointers in a node because you have two pointers, the next and previous. And then a linked list in which the last node points to the first node is called the circular linked list, which is the one we just discussed now. Okay, so we are out of time and we finished these slides. So on Monday, we will start on complexity analysis with Prof. Coulter. Thank you very much for your time and see you later during the practical session.